Welcome back. In this tutorial of Hierarchical Deep Learning Neural Network, HiDeNN, I want to extend the finite element method into the neural networks. Let's begin. So the key idea of HiDeNN is to rewrite the finite element interpolation functions as a neural network. So going back to the element-wise interpolation function, it was piecewise linear, right? We can formulate a neural network that exactly the same as this finite element interpolation, like this. So it consists of two hidden layers. They are partially connected, and their weights and biases are functions of nodal coordinates and nodal variables, displacement field, displacements. Remember, they are not independent, especially those weights and biases of the first two hidden layers. They are functions of nodal coordinates. So how can we formulate the weak form neural network? We call the entire stuff as HiDeNN using this element-wise neural network. It is shown as this. So this element-wise neural network goes into the element, but we have multiple elements, right? And in this previous example, we had element 1 through element 4. And finally, we formulate the loss function, which is the potential energy. So this is a key statement. The loss function of HiDeNN is the potential energy of the weak form of the equation. By the principle of minimum potential energy, we can find the solutions by minimizing the potential energy. This is exactly what we do in FEM. But now we want to do this, we want to interpret this as a neural network. So as an elementary neural networks, weights and biases, you can see here, they are functions of nodal displacement u and nodal coordinate x. You can actually find both the solution, which are nodal displacement, and the optimal nodal coordinates, which are the x. So let's assume that we just fix these nodal coordinates and only optimize for nodal variables, nodal displacement. Then the entire HiDeNN FEM scheme, this one, is exactly the same as finite element. You see, we just saw that in finite element, we try to optimize the potential energy with respect to the nodal displacement, u. But if you formulate in this way, you have the additional possibility of optimizing the nodal coordinates. That's the key idea of HiDeNN FEM. So if you do that, before we go, I want to start from the non-uniform mesh, because if we start from the uniform mesh, there's no room for the mesh optimization. So I just want to show this case with non-uniform mesh first. Now comes with the HiDeNN FEM. So HiDeNN FEM is colored green, and after solving this HiDeNN FEM, you'll be able to see here where the nodal coordinates are moving toward the uniformly spaced distribution, which is the best one, actually, with only 4 elements. So you can see the errors are lower than finite element, of course. So basically, HiDeNN FEM and HiDeNN FEM, we can solve nodal solutions and also optimize the nodal coordinates at the same time. That is the message of this tutorial. All right. So let's go to the program. I want to change this HiDeNN to first. It was first, but now it is true, right? And also change this true. I want to start with a non-uniform mesh. So I will run this, and you will see a new results, right? As you can see there, yeah, we are optimizing the nodal coordinates here. And finally, we have this solution, right? We started with a non-uniform mesh. Actually, they are randomly seeded, so the numbers are slightly different, but the idea is clear, right? So even though we started from a non-uniform mesh, you'll be able to find out the optimal one, the best one, which is the uniformly spaced meshes. Okay, that's it for this tutorial, and hope you see the next one, which is the convolution HiDeNN. Thank you.